The modern industrial and construction landscape is characterized by an ever-increasing demand for the movement and assembly of colossal structures. From the assembly of offshore oil rigs to the construction of towering skyscrapers, the need for precise, reliable, and powerful equipment has never been greater. Super cranes and self-propelled transport modules, SPTMs, have become indispensable tools in the engineering world, allowing the construction and industrial sectors to push the boundaries of what is possible. This essay delves into the technological marvels of super cranes and SPTMs, exploring their role, functionality, innovations, and the profound impact they have on global industries. The evolution of heavy lifting and transport. The history of heavy lifting and transport dates back to ancient times when rudimentary cranes and sledges were used to construct monumental structures like the pyramids of Egypt. Over the centuries, advancements in engineering have led to the development of more sophisticated machinery capable of handling increasingly heavy loads. The advent of the Industrial Revolution marked a turning point in this evolution, as steam-powered cranes and rail systems began to dominate the landscape of heavy lifting and transport. The 20th century saw the introduction of hydraulics and electrical systems, which revolutionized the capabilities of cranes and transport vehicles. By the latter half of the century, the construction of massive infrastructure projects such as dams, bridges, and skyscrapers necessitated the development of even more powerful and versatile machinery. This period marked the birth of what we now refer to as super cranes and the modern SPTM. Super cranes. Titans of modern construction. Crawler cranes. Mobility and power combined. Crawler cranes represent one of the most versatile and powerful types of cranes used in modern construction. These cranes are mounted on a set of tracks, which provide them with mobility and stability, allowing them to traverse rough terrain with heavy loads. The crawler crane's design is inherently robust, with a low center of gravity that makes it particularly well suited for lifting extremely heavy loads. One of the most significant advancements in crawler crane technology is the development of modular boom systems. These systems allow cranes to be configured for different lifting capacities and heights, making them adaptable to a wide range of projects. For instance, the Liebherr LR13000, one of the largest crawler cranes in the world, can lift up to 3,000 tons and reach heights of over 240 meters. This crane has been used in some of the most challenging projects, including the construction of nuclear power plants and the assembly of offshore platforms. Crawler cranes are also equipped with advanced control systems that enhance their precision and safety. These systems use a combination of sensors, cameras, and software to monitor the crane's operation in real time. This allows operators to make precise adjustments to the crane's movements, ensuring that heavy loads are lifted and placed with the utmost accuracy. The ability to control these cranes remotely further enhances safety, as operators can position themselves in locations where they have a clear view of the operation without being exposed to potential hazards. Tower cranes, building the world's skyscrapers. Tower cranes are an essential tool in the construction of tall buildings, including skyscrapers, which define modern cityscapes. These cranes are designed to lift heavy materials such as steel beams, concrete, and glass panels to great heights, making them indispensable in high-rise construction. The design of tower cranes is both elegant and functional. The mast, or tower, of the crane is anchored to a concrete base, providing the stability needed to lift heavy loads. The jib, or horizontal arm, extends from the mast and can rotate 360 degrees, allowing the crane to cover a large area. The counterjib, located on the opposite side of the mast, balances the crane by holding the counterweights. One of the most remarkable aspects of tower cranes is their ability to grow as the building rises. This is achieved through a process known as climbing, where additional mass sections are inserted below the slewing unit, raising the crane's height. This allows the crane to remain functional throughout the construction of tall buildings, such as the Burj Khalifa in Dubai, where cranes were used to lift materials to heights exceeding 800 meters. Modern tower cranes are equipped with sophisticated control systems that allow for precise movement and placement of loads. These systems often include anti-collision technology, which is crucial in urban environments where multiple cranes may be operating in close proximity. The automation of certain functions, such as load hoisting and jib rotation, reduces the risk of human error and enhances overall safety. Floating cranes, masters of the maritime environment. Floating cranes, also known as crane vessels, are specialized cranes mounted on ships or barges. These cranes are designed to operate in maritime environments, where they are used for the construction and maintenance of offshore structures, including oil rigs, wind turbines, and bridges. One of the primary advantages of floating cranes is their ability to lift extremely heavy loads in challenging environments. These cranes are often used in offshore oil and gas projects, where they lift and install large modules and topsides weighing thousands of tons. The Thialf, one of the most powerful floating cranes in the world, has a lifting capacity of 14,200 tons and has been instrumental in numerous offshore installations. Floating cranes are also used in the construction of bridges that span large bodies of water. For example, the construction of the Akashi Kaikyo Bridge in Japan, the world's longest suspension bridge, required the use of floating cranes to lift and place the massive bridge segments. These cranes were able to operate in deep water, where traditional land-based cranes would have been ineffective. The operation of floating cranes is highly specialized and requires careful planning and execution. Factors such as sea state, wind speed, and tidal conditions must be considered when lifting heavy loads at sea. To ensure stability, floating cranes are often equipped with ballast tanks that can be filled with water to lower the center of gravity. Additionally, dynamic positioning systems are used to maintain the crane's position during lifting operations, even in rough seas. Ring cranes, the pinnacle of lifting power. Ring cranes are among the most powerful and impressive lifting machines ever created. These cranes are mounted on a circular track known as a ring, which allows them to rotate 360 degrees while carrying ultra-heavy loads. Ring cranes are used in some of the most demanding construction projects, including the assembly of large industrial plants, nuclear power stations, and offshore platforms. The design of ring cranes is characterized by their massive size and lifting capacity. The Cranes SGC 250, also known as Big Carl, is the world's largest ring crane, capable of lifting 5,000 tons to a height of 250 meters. Big Carl was used in the construction of the Hinkley Point C nuclear power station in the UK, where it lifted and placed enormous prefabricated sections of the reactor buildings. Ring cranes are equipped with advanced lifting systems, including multiple winches and hoists, that allow them to distribute the load evenly across the crane structure. This is essential for maintaining stability and preventing structural failure during lifting operations. The crane's circular track provides unparalleled maneuverability, allowing it to lift and place loads with extreme precision. The operation of ring cranes requires meticulous planning and coordination. Engineers use sophisticated modeling and simulation software to design lifting operations, taking into account factors such as load distribution, wind forces, and ground stability. These simulations allow engineers to identify potential risks and develop strategies to mitigate them, ensuring the safe and efficient operation of the crane. Self-propelled transport modules, SPTMs, revolutionizing heavy transport. Design and engineering of SPTMs, self-propelled transport modules, SPTMs, are specialized vehicles designed for the transportation of extremely heavy and oversized loads. These vehicles are modular, meaning they can be configured in various ways to accommodate different types of loads. The modular design allows SPTMs to be assembled into large transport platforms capable of carrying loads weighing thousands of tons. Each module in an SPTM is equipped with multiple axles, each of which has its own steering and suspension system. This allows the vehicle to distribute the weight of the load evenly across its axles, reducing the risk of damage to both the load and the road surface. The suspension system is designed to adapt to the terrain, ensuring that the vehicle remains stable even when traversing uneven ground. SPTMs are self-propelled, meaning they have their own power sources, typically diesel engines or electric motors. These power sources drive the wheels and provide the necessary torque to move heavy loads. The vehicle's movement is controlled by a central control system, which can be operated remotely or by an onboard operator. The control system allows for precise adjustments to the vehicle's speed, direction, and braking, ensuring that the load is transported safely and efficiently. One of the key innovations in SPTM design is the development of multi-directional steering. This allows the vehicle to move in any direction, including sideways and diagonally, which is particularly useful when maneuvering in tight spaces. Multi-directional steering is achieved through the use of hydraulic or electric actuators that control the angle of each wheel independently. Applications of SPTMs in global industry. SPTMs are used in a wide range of industries, each of which has unique requirements for heavy transport. These industries include shipbuilding, aerospace, energy, and infrastructure construction. Shipbuilding. In the shipbuilding industry, SPTMs are used to transport large sections of ships from the assembly area to the dry dock. These sections, known as blocks, can weigh thousands of tons and must be transported with extreme care to avoid damage. SPTMs are ideal for this task because they can be configured to match the shape and size of the block, ensuring even weight distribution and minimizing the risk of deformation. Aerospace. The aerospace industry also relies on SPTMs for the transport of large and delicate components, such as aircraft fuselages and wings. These components are often transported from the manufacturing plant to the assembly facility, where they are integrated into the final aircraft. The precision and stability offered by SPTMs are crucial in ensuring that these components arrive at their destination without damage. Energy. In the energy sector, SPTMs play a critical role in the transport of heavy equipment, such as transformers, generators, and turbines. These components are often transported to remote locations, such as power plants or substations, where they are installed and connected to the grid. The ability of SPTMs to navigate challenging terrain and deliver loads with precision makes them indispensable in this industry. Infrastructure construction. The construction of large infrastructure projects, such as bridges, tunnels, and dams, often requires the transport of oversized components, such as bridge segments, tunnel boring machines, and dam gates. SPTMs are used to transport these components from the manufacturing site to the construction site, where they are assembled and installed. The modularity and versatility of SPTMs allow them to handle a wide range of loads, making them a valuable asset in infrastructure construction. Case studies. SPTMs in action. The transportation of a giant generator. One of the most impressive examples of SPTMs in action is the transportation of a giant generator for a power plant in Germany. The generator, which weighed over 800 tons, needed to be transported from the manufacturing plant to the power plant, a journey of over 200 kilometers. The route included narrow roads, bridges, and tunnels, making the transport a highly challenging operation. To transport the generator, a fleet of SPTMs was assembled into a large transport platform, with each module configured to distribute the weight of the load evenly. The transport operation was meticulously planned, with engineers using simulation software to map out the route and identify potential obstacles. The SPTMs were equipped with multi-directional steering, allowing them to navigate tight corners and avoid obstacles along the route. The transport operation took several days to complete, with the SPTMs traveling at a slow and steady pace to ensure the safety of the load and the surrounding infrastructure. Throughout the operation, the movement of the SPTMs was monitored in real time, with engineers making adjustments as needed to maintain stability and prevent accidents. The successful transport of the generator was a testament to the capabilities of SPTMs and the importance of careful planning and execution in heavy transport operations. The assembly of an offshore wind farm. The construction of offshore wind farms is another area where SPTMs have proven to be invaluable. These projects involve the transport and installation of large wind turbine components, such as towers, nacelles, and blades, which can weigh several hundred tons each. In the assembly of the Hornsea Project 1 wind farm in the UK, SPTMs were used to transport the wind turbine components from the manufacturing site to the port, where they were loaded onto installation vessels. The SPTMs were configured to match the shape and size of the components, ensuring that they were transported safely and securely. The transport operation was complicated by the need to navigate narrow roads and sharp turns on the way to the port. The multi-directional steering and precise control offered by the SPTMs were crucial in overcoming these challenges. Once at the port, the components were loaded onto the vessels using cranes, after which they were transported to the installation site in the North Sea. The successful assembly of the Hornsea Project 1 wind farm, which is now one of the largest offshore wind farms in the world, was made possible by the use of SPTMs. These vehicles played a critical role in ensuring that the wind turbine components arrived at the installation site on time and in perfect condition. Technological innovations and future trends. Advanced control systems and automation. One of the most significant areas of innovation in the design and operation of supercranes and SPTMs is the development of advanced control systems and automation. These systems use a combination of sensors, cameras, and software to monitor and control the movement of the machines in real time, enhancing precision and safety. In supercranes, advanced control systems allow operators to make fine adjustments to the crane's movements, ensuring that loads are lifted and placed with pinpoint accuracy. These systems also include features such as load monitoring, which provides real-time data on the weight and distribution of the load, and anti-sway technology, which reduces the oscillation of the load during lifting operations. Automation is playing an increasingly important role in the operation of supercranes and SPTMs. In some cases, these machines can be operated remotely, allowing operators to control them from a safe distance. This is particularly valuable in hazardous environments, such as offshore oil rigs or nuclear power plants, where the safety of personnel is a primary concern. The use of artificial intelligence, AI, in the operation of supercranes and SPTMs is another area of ongoing research and development. AI can be used to analyze data from sensors and cameras, identifying patterns and making predictions that can help operators make better decisions. For example, AI algorithms can be used to predict the behavior of the load during lifting or transport, allowing operators to make adjustments before problems arise. Environmental considerations and sustainability. As industries around the world strive to reduce their environmental impact, The design and operation of supercranes and SPTMs are increasingly influenced by considerations of sustainability. This includes the development of more fuel-efficient engines, the use of alternative energy sources, and the implementation of practices that reduce emissions and minimize waste. One area of focus is the reduction of fuel consumption in SPTMs. Traditional SPTMs are powered by diesel engines, which are known for their high levels of emissions. To address this issue, manufacturers are developing hybrid and electric SPTMs, which use a combination of diesel and electric power to reduce fuel consumption and emissions. These vehicles are equipped with energy recovery systems that capture and store energy generated during braking, which can then be used to power the vehicle. In the case of supercranes, efforts are being made to reduce the environmental impact of lifting operations. This includes the use of lightweight materials in crane construction, which reduces the amount of energy required to operate the crane. Additionally, manufacturers are developing cranes that can be powered by renewable energy sources, such as solar or wind power, reducing the reliance on fossil fuels. The implementation of environmentally friendly practices is also becoming more common in the operation of supercranes and SPTMs. This includes the use of biodegradable lubricants, the recycling of materials, and the adoption of best practices for waste management. These efforts are part of a broader industry trend toward sustainability, which seeks to minimize the environmental impact of construction and industrial operations. The future of heavy lifting and transport. The future of heavy lifting and transport is likely to be shaped by a combination of technological innovation and the evolving demands of global industries. As projects continue to grow in scale and complexity, the need for more powerful, precise, and efficient equipment will drive the development of new technologies and practices. One of the key trends in the future of heavy lifting and transport is the increasing use of digital technologies. This includes the integration of digital twins, which are virtual models of physical assets, into the design and operation of supercranes and SPTMs. Digital twins allow engineers to simulate and analyze lifting and transport operations in a virtual environment, identifying potential risks and optimizing performance before the operation takes place. Another trend is the growing importance of sustainability in heavy lifting and transport. As industries face increasing pressure to reduce their environmental impact, the development of more sustainable equipment and practices will become a priority. This could include the use of alternative energy sources, the implementation of circular economy principles, and the adoption of best practices for resource management. In terms of equipment design, the future is likely to see the development of even larger and more powerful supercranes and SPTMs. These machines will be capable of handling the most demanding projects, including the construction of megastructures such as spaceports, floating cities, and offshore energy islands. The integration of advanced control systems, automation, and AI will further enhance the capabilities of these machines, making them even more precise, efficient, and safe. Conclusion. The role and function of supercranes and self-propelled transport modules, SPTMs, in lifting and transporting supergiant objects in construction and industry are of paramount importance. These machines have transformed the way we build and maintain the world's infrastructure, enabling the completion of projects that were once thought impossible. From the towering skyscrapers that define our cities to the vast offshore platforms that power our economies, supercranes and SPTMs are at the heart of the modern industrial landscape. As we look to the future, the continued evolution of these machines will play a crucial role in meeting the challenges of the 21st century. Technological innovation, sustainability, and the increasing complexity of global projects will drive the development of new and improved supercranes and SPTMs. These machines will continue to push the boundaries of what is possible, enabling the construction and industrial sectors to achieve new heights in efficiency, safety, and environmental performance. In conclusion, supercranes and SPTMs are not just tools of construction and industry. They are the engines of progress, driving the development of our world and shaping the future of global infrastructure. Their role in lifting and transporting supergiant objects is critical to the continued growth and advancement of our societies, and their impact will be felt for generations to come.